Have you ever wondered what reality is? How the universe works at its most fundamental level? Enter quantum mechanics, the theory that seeks to answer these profound questions. It's a realm of physics that delves into the behavior of the smallest particles in the universe. We're talking atoms and even tinier constituents known as subatomic particles. It's here that a fundamental shift in our understanding of nature occurs, a departure from the safe harbor of classical physics. Quantum mechanics doesn't just describe particles as tiny billiard balls or minuscule points in space. It paints a much more complex and, dare we say, bizarre picture. In this world, particles can be in multiple places at the same time, teleport instantly across vast distances, and even exist in states of being both dead and alive. So, are you ready to dive into the world of quantum mechanics? Imagine a particle that can act both as a particle and a wave. Sounds strange, right? Welcome to the world of quantum mechanics and the concept of wave-particle duality. This concept tells us that particles like electrons can behave both as particles and as waves. Let's take the famous double-slit experiment as an example. When particles are fired at a barrier with two slits, they don't behave as we'd expect particles to. Instead of forming two straight lines on the wall behind, they create an interference pattern, just like waves would. But here's the kicker. If we try to observe which slit the particle goes through, it behaves like a particle again, forming two lines instead of an interference pattern. This experiment shows us that the act of observation changes the behavior of the particle. So, particles can act like waves, and waves can act like particles. This is one of the most fascinating aspects of quantum mechanics. What if energy could only exist in certain specific levels? Sounds strange, but that's the reality in the quantum world. Unlike classical physics, which allows for a continuous change in energy levels, quantum mechanics introduces us to the concept of quantized energy levels. Picture this. Imagine energy as a staircase. In classical physics, energy could be anywhere along the staircase, smoothly moving up or down. But in quantum mechanics, energy can only exist on the steps. You can be on the first step, the second step, and so on, but never in between. These steps represent the quantized energy levels. The behavior of electrons around an atomic nucleus perfectly exhibits this concept. Electrons exist in specific energy levels and can only jump from one level to another, absorbing or emitting energy in the process. This concept, the quantization of energy, is another fundamental aspect that sets quantum mechanics apart from classical physics. How about a world where the more precisely you know one thing, the less precisely you can know another? Welcome to the realm of the Heisenberg uncertainty principle, a mind-bending concept in the world of quantum physics. Introduced by Werner Heisenberg, this principle states that it's impossible to simultaneously measure the exact position and momentum of a particle with absolute certainty. Imagine you're trying to pinpoint a particle's location. The more accurately you determine its position, the more its momentum becomes a blur. Conversely, if you measure its momentum with precision, its position gets hazy. It's like trying to juggle two balls with one hand. The better you get at one, the other slips away. This isn't due to any technological limitations, but is embedded in the very fabric of nature. It's a fundamental truth about the universe, a universe where certainty gives way to probability. This principle fundamentally changes our understanding of how we can measure and know the universe. Can something be in two places at once? Can two particles be mysteriously connected no matter how far apart they are? Welcome to the weird world of quantum superposition and entanglement. Take a moment to imagine a coin spinning in the air. While it's spinning, before it lands, we can't say for certain if it's heads or tails. It's in a superposition of states, it's both, until we catch it and see the result. This is a simple way to understand quantum superposition. But in the quantum world, it's not just a lack of knowledge about the state. Quantum particles literally exist in multiple states simultaneously until they're measured. And this leads us to the concept of quantum entanglement, a phenomenon so strange that even Einstein called it spooky action at a distance. Imagine two entangled particles. No matter how far apart they are, the state of one instantly influences the state of the other. If we measure one particle and find it spinning in one direction, the other particle will immediately be found spinning in the opposite direction. This instantaneous connection happens faster than the speed of light, defying our classical understanding of how information can travel. This isn't just theoretical. Quantum entanglement has been experimentally confirmed time and time again, most famously by the Bell's theorem experiment. And it's not just a quirky quirk of the quantum world. Quantum entanglement is a key principle behind emerging technologies like quantum computing and quantum cryptography. But how can something be in two places at once? How can two particles be mysteriously connected no matter how far apart they are? These are the questions that quantum mechanics forces us to ask. They challenge our classical notions of reality, of locality, of causality. They force us to accept that at its most fundamental level, the universe is not as it seems. These concepts are at the heart of quantum mechanics, and they continue to baffle and fascinate scientists today. What happens when you measure a quantum particle? This question brings us to the heart of one of the most baffling aspects of quantum mechanics, the quantum measurement problem. In the quantum realm, the act of measuring a particle is not as straightforward as it might seem. When we measure a particle, we force it to collapse from a state of superposition, where it can exist in multiple states at once, into a single definite state. But here's where things get intriguing. The exact mechanism behind this collapse and why it occurs is still a topic of hot debate among physicists. This leads to multiple interpretations, such as the Copenhagen interpretation, which suggests the act of observation causes this collapse, and the many worlds hypothesis that proposes each measurement splits the universe into multiple parallel realities. Measurement in quantum mechanics is a complex and intriguing issue that continues to puzzle scientists. With each measurement, we are peering into the strange and counterintuitive world of quantum mechanics, a world that continues to fascinate and perplex us. How can understanding quantum mechanics help us in the real world? Quantum mechanics, this abstract world of probabilities and paradoxes, might seem far removed from our daily lives. But what if I told you that these principles, these strange behaviors of the microscopic world, could revolutionize computing as we know it? Welcome to the world of quantum computing. This is where the principles of quantum mechanics meet the practical world. Unlike classical computers, which use bits as their smallest units of information, quantum computers use quantum bits or qubits. A classical bit can be either 0 or 1, but a qubit, thanks to the principle of superposition, can be both 0 and 1 at the same time. Imagine it as being at two places at once, or doing two tasks simultaneously. This ability of qubits to exist in multiple states allows quantum computers to process large amounts of information at once. It's like having thousands of computers working in parallel, making certain computations significantly faster than classical computers. But it doesn't stop there. Quantum entanglement, that spooky action at a distance, comes into play as well. In a quantum computer, qubits can become entangled, meaning the state of one qubit can instantly affect the state of another, no matter how far apart they are. This interconnectedness brings about a level of synchronicity and coordination that's simply impossible in classical computing. Quantum computers, however, are not just faster versions of our current computers. They open up new possibilities, from simulating complex quantum systems, which could revolutionize drug discovery and material science, to solving optimization problems, which have applications in logistics, finance, and artificial intelligence. But let's be clear, we are still in the early days of quantum computing. Building a practical quantum computer is a colossal challenge, as quantum systems are delicate and prone to errors. Yet the potential is enormous. As we continue to unravel the mysteries of the quantum world, we are inching closer to the quantum revolution in computing. Quantum mechanics, once thought to be purely theoretical, is now becoming practical in the form of quantum computing. Quantum mechanics is a fascinating field that fundamentally changes our understanding of the universe. At its heart, it presents a dichotomy, the wave-particle duality, where particles like electrons exhibit both wave-like and particle-like properties. It also introduces us to the concept of quantized energy levels, a departure from the continuous energy changes allowed in classical physics. The Heisenberg uncertainty principle then tells us about the inherent limits in knowing certain pairs of properties of a particle. Quantum superposition and entanglement take us further down the rabbit hole, with particles existing in multiple states at once and the state of one instantly influencing another, no matter the distance. The act of measuring these quantum systems is a unique process, collapsing the superposition of states into a definite outcome. Finally, we touch on quantum computing, where quantum bits can exist in multiple states simultaneously, paving the way for faster computations. Quantum mechanics challenges our understanding of reality and continues to be an exciting field of study with many unanswered questions.